This video is about how to relate physics to maths using Newton's second law. And then using that maths to work out how something will behave, where it will go, how fast and when. We've been thinking about a spacecraft falling towards Earth. Let's think about how we might model this. We've said that forces acting are drag and weight. Newton's second law tells us that force equals mass times acceleration. How can we turn this into an equation that we can solve? We know that the weight, mg, is constant in this case. We need an expression for the drag. We need a model. Experiments have shown that drag is proportional to velocity squared. So let's try that. We also know that acceleration is rate of change of velocity with respect to time. So let's try that too. Force becomes weight minus drag, and acceleration becomes dv by dt. We've now got a differential equation, and if we can work out how to integrate it, we can work out what the velocity will be at any time. So how do we do it? That's a difficult one. For differentiation, we just follow the rules, but integration is reverse engineering of differentiation. We know how to solve differential equations by recognizing what type they are and then employing an appropriate method to solve them. This one's fairly simple to begin with. It looks like we can separate variables to get t on one side of the equation and v on the other side, and then integrate both sides. Integrating the left-hand side is simple. Integral dt is just t plus constant. Integrating the right-hand side, however, takes more skill. First, let's get rid of the system parameters g, m and k by making the substitution x squared is equal to k over mg times by v squared, and that gives dx is equal to k over mg all square rooted times by dv. So our integral becomes square root of m over gk times by the integral of 1 minus x squared. So now we've got this integral 1 over 1 minus x squared. How do we do it? Any ideas? So this is where experience comes in, and we find the answer essentially by guessing it. Try the substitution x equals tanh y. Now it's all about how well you know your hyperbolic functions. Dx becomes sec squared y dy, and 1 minus x squared becomes 1 minus tanh squared y. So we substitute it into our differential equation here. Hyperbolic functions behave similarly to trig functions. So where cos squared theta plus sine squared theta equals 1, we have cos squared theta minus sine squared theta is 1. And if we divide this through by cos squared theta, we end up with the relationship 1 minus tanh squared theta is sec squared theta. We can substitute this in here. We're left with m over gk all square rooted times sec squared y dy divided by sec squared y. These terms cancel, and we're just left with t plus a constant is equal to m over gk all square rooted times the integral dy, which is t plus constant equals m over gk all square rooted times by y. Now we need to back substitute y for x and x for v. So we have, if x is tanh y, y is inverse tang of x. So this becomes t plus a constant is equal to m over gk all square rooted times by inverse hyperbolic tangent of k over mg all square rooted times by v. So we've almost got our solution. Let's assume that at t equals 0, the velocity also equals 0. And that implies that this constant here equals 0 as well. If we set that equal to 0, we can rearrange this to end up with our final solution of v in terms of t. So v is equal to square root of mg over k times the hyperbolic tangent of gk over m all square rooted times t. And we can draw that and it looks like this.